Thank you, and thank you for all of those who braved the fake snowstorm. These guys, they have, it's probably something to do with their numerical methods for solving these equations. I think MIDA turned to the study of solution of climate equations. Okay, so all this that I'll have to say today is joint with Igor Wigman. I'll try to describe to you some picture, but of the picture, I think you'll see that there are millions of really basic questions that this asks more questions than it answers. I'll answer one question only. My interest in studying the zero set of a function or of a random real polynomial, the word real is very critical in this talk. Everything's about real, not complex. I'm going to look at real zeros, real roots, real varieties, and zero sets of real eigenfunctions. One of my favorite objects are mass forms on the modular group, which are highly excited vibrating states, which have many properties in terms of their eigenvalues, Hecker eigenvalues. The question of their nodal, the distribution or the count of their nodal domains is something that we have seen pictures of for many years but never been able to say anything. The problem is so difficult that I eventually decided to try and understand even what the expected answer should be. And the expected answer is a purely probabilistic question. What happens with a random monochromatic wave? I'll explain what that is in a minute. And usually, if you're working in the theory of numbers and you need some probabilistic model, usually the probability theory is pretty straightforward. Occasionally it's tricky, like when Nick Katz and I were looking at zeros of polynomial, of zeta functions of curves over finite fields, we actually needed to know something about the zeros of random eigenvalues of random matrices, and while I think the mathematical community thought that this was all hokey pokey, we studied a bit of Dyson and Gordon's work and saw that everything was quite rigorous, though it seems that most people had decided it wasn't until after us. So the probability theory was there for us to use. So even though that was already a more sophisticated theory, usually the probability theory is quite easy from a probabilist point of view. The question I'm going to describe today, the probabilists apparently don't know much about this, and in fact we're going to answer some questions, and so I'm glad there are a few statistical physicists and probabilists here. Maybe they'll be able to turn this into a real theory. Along the way, in studying these monochromatic waves, so this is all about random functions, it was clear that a very closely related question is what's the topology of a random real variety? And I'm going to answer that. So there's a universal distribution of topologies of a random real variety, completely universal. There's no two choices about it. And that seems to be a rather interesting question. So let me start with one variable, where this all goes back to Mark Katz, not Nick Katz, who started the subject. And there's some famous Katz-Rice formula, which I want to explain to you, which is the fundamental tool in the subject, but it can only answer one kind of question and not about the topology. So suppose I have a function of one variable, which means a polynomial of degree t in one variable. Everything's real. Throughout this talk, v of f, if I'm given a polynomial or more generally a function on a manifold, the zero set of the function, as I said, everything's real. The zero set will be denoted by v of f. You may wonder that this set's going to be singular and things like that, but we're going to be looking at a random f. I'm going to define random. Random is the most important thing. That's something we choose. We play God as to what is random. Anyway, once I define the notion of random, the typical member in the random guy, v of f, will be non-singular. So the zero set will be always a smooth real manifold. In this case, in one variable, the zero set would be a bunch of points. There won't be repeated roots. And the only thing you want to know about this set, well, you could ask for their location, but I'm interested in the topology of the zero set of a function. So the cardinality, the number of zeros, is all you might ask about here. And that's what Mark Katz started. A theory, a quite beautiful theory, developed further by Rice and many other people. So let me look at the vector space of real polynomials of degree t. And when I say random, I have to give you a probability measure on the space that I'm talking about, which in this case is a linear real vector space. Now, I'm only going to look at Gaussians, only Gaussian distributions. That's not perhaps completely satisfying, but the questions are sufficiently difficult for Gaussians that we're going to stick to Gaussians. Once we understand Gaussians, I can imagine there being a whole discussion of what of this is universal. I don't know. I barely know what's going on. I know very little, as you'll see, for Gaussians, but I'm going to stick to a Gaussian. Now, to give a Gaussian is to give a measure which is of the form e to the minus length squared times a Haar measure, in this case, the Haar measure on the vector space is a real vector space. So giving a Gaussian is the same as giving an inner product. So the question is, what inner product do you want to use on your vector space here to define the notion of random? And Mark Katz, of course, chose one. I'll call it the naive model. It's poor from many points of view. He recognizes it's poor. It's poor from the point of view of creating zeros. Let me explain what I mean by that. So if you go back here, or the inner product he chose on the vector space, W1T, the first one, and the one that's most studied in the literature, is just the inner product of the coefficients, the naive inner product. This is equivalent, and so he wouldn't have stated it this way. He'd have stated a much more basic thing. If I give you a random polynomial, I think most of you would say, write the polynomial down at random, choose the coefficients at random, right? But by just writing it down, you've already favored something. You've already made a big mistake, just writing it down. So his notion of random is the standard inner product, and the standard inner product is to put the AJs to be Gaussian variables. So all my Gaussians will be centered zero, zero-centered. I don't want you to make the mean very large and push things out for no good reason, because I'm looking at the zero set. So everything will be centered at zero. That's given. And then a Gaussian with this inner product, or this with a naive choice, is the model he looked at. And he developed a thing which is called the Katz-Rice formula, which will allow you to compute how many zeros a random real polynomial has. So the AJs, let me repeat, in the naive model are chosen to be Gaussian, mean 0, variance 1. Same variance. That's all you need to know. I'll discuss in a minute what happens there, but you can see why this is a bad choice, because the zeros are going to be, let me go back again one more time. The zeros, I'm looking at f of x equals summation aj x to the j. Suppose I ask whether I vanish at the origin. Well, that'll only depend on a zero. That should start at 0. Only depend on a 0. Otherwise, you factor out an x. So it would only depend on a 0. While at infinity, only the big coefficients would play a role. So there's no serious statistics going on here. And it's clear that if f is going to have many zeros, the only place where all these are roughly the same size will be when x is plus or minus 1. So in fact, most of the zeros are very near 1 and minus 1. And what you've taken is projective space, which is the line together with a point at infinity, which is where the zeros are supposed to lie. And you've decided to make a model where all the zeros are plus or minus 1. And of course, you have very few zeros as a consequence. Of course, you can have at most t real zeros. I'll tell you the answer in a minute. But that is the weakness of this model, in that you haven't made the projective space, the place where the zeros are supposed to lie, look homogeneous. Each point should look like every other point. So I'll call the real Fubini Study ensemble, a big name for this one-dimensional thing, but the minute I go to several variables, which will be in a second, this will be completely natural, is the real Fubini Study will be, first let's homogenize. So instead of looking at having taken x1 to be 1, which doesn't matter if we're just counting zeros, but in terms of this random model of trying to make all the points in P1 look the same, I want to put an inner product on the space of homogeneous polynomials of degree t in 2 variables. That's what this one variable situation is. And the natural inner product, which I'm calling the real Fubini Study inner product, is to take some integral to just define f times g. Remember, f and g are homogeneous. So this will pull out a factor times the integral of f of x times g of x against a measure on the sphere, or on the projective line, which is the sphere mod x in 2 dimensions divided by plus minus 1. And the important thing is I'm making this thing here uniform. And in higher dimensions, I'll be taking the round metric on projective space, the constant curvature metric, which makes every point look like every other point. This essentially defines a unique probability inner product. Notice I don't want to change the inner product for each degree, because, I mean, I could always, you could always make a Gaussian concentrate at a point. So I'm not going to make statements which are true for every Gaussian. You want to define the Gaussian, which is uniform once and for all. And throughout, the most important, the relevant thing I'll be talking about is this real Fubini Study Gaussian. And it certainly doesn't favor one point to another point. So this is a quite different inner product to the inner product that I put, the naive inner product that Mark Katz put on. I'll describe the Katz-Rice formula because I want to describe theorems that go way beyond the Katz-Rice formula. So I think I should explain what this Katz-Rice formula is. But it's a remarkable formula, and that was Katz's theory, to compute any statistic in one variable about the number of zeros. So the first thing he computed was how many zeros does a typical F have? Yeah. Yes, F and G are in W1T, homogeneous of degree T. This is the inner product on W1T. To say that there's an answer, of course I'm going to make a polynomial have a higher and higher degree, otherwise there's no universal answer. You could ask, there are many number theorists in this audience, if you draw an elliptic curve, do you draw it with one component or two components? Well, if you take the naive model, there's going to be no universal answer for plane cubics. But if you take the naive model, you should draw one component because the probability is slightly bigger than a half in that case. And if you take the real Fubini Study model, which tries to create more zeros, you should draw two components. If you've ever wondered.
Is this homogenization related to making A's complex Gaussian variables?
No, absolutely not. I'm going to show you. Katz tried to do something along these lines. I'll show you in a second. Yeah. All right. He was very disappointed. They only log T zeros. And I mean, I've sort of indicated to you why they only log T zeros, because all the zeros want to be plus or minus 1. And that's what they're all very near plus or minus 1 with a very small scale. You should be happy they log T zeros. That's how many you get near a point. But in the real Fubini Study metric, I'll show you how you compute that in a minute, you get T over root 3 zeros rather than, so you now get many more zeros. So you're getting some 66% of the maximum number of zeros that can happen. Keep that in mind because I'm going to try to answer that question for curves in the plane. How many ovals does a random plane curve have compared to the maximum, which Sarnak gave an inequality for the maximum number of ovals? All right, and what happens here is in this case where in this naive model, we're making one x squared, x cubed orthogonal and taking the coefficients at random, which is completely the way mankind wants to write down a polynomial. If you take the real Fubini Study and you use Gram-Schmidt, you can always take one of these Gaussians and then use Gram-Schmidt to diagonalize and then make the coefficients standard Gaussians. Then a simple diagonalization process shows that in the real Fubini Study, instead of taking the polynomials on the projective, you're now looking at polynomials on the projective line, which is just a circle with plus minus 1 identified. You're looking at cosine and sine. And those functions are much better behaved around the circle, on the circle, than x to the n and y to the n on the real line. So that's why there are many more zeros. And of course, they don't have a random real polynomial. You shouldn't expect it to have 100% zeros on the in the projective line. Okay, so let me say a word about this Katz-Rice, because that's the standard tool. And if you look at the theory of zero sets of polynomials, almost all this topic that you'll find a massive literature, and it's this Katz-Rice formula and its generalization to several variables. The idea is if I take something in W1T or anything I write down later, and I fix a point x and I take f of x. So now this is a scalar valued variable, which is a linear function on a Gaussian space. So it's itself a Gaussian mean 0. So the only thing I need to know about the what f of x looks like, which is a Gaussian of mean 0, is what its variance is. So the thing that's most important when you want to compute anything, you start to compute, is the covariance which is the expected value over the ensemble, whatever the probability with Gaussian is, of f of x times f of y, which I'll call ktxy, which you can usually compute explicitly. So if you have summation ajx to the j, and then you have summation bkx to the k, and you take the product and take expectation, use the independence of xj and aj and bk, you'll get just the diagonal, and you'll get something that presumably you can add up. That's Katz's first observation. So this ktxy here, we will need to always study this covariance function, which is a point pair function on our space, as t goes to infinity. In different settings, this almost always becomes some semi-classical asymptotics, something interesting. In random matrix theory, those who've seen random matrix theory, this is very similar to the Gaussian getting down to the asymptotics of the kernel after using orthogonal polynomials. How do you use this tells you what f of x is looking like, and maybe f of y near x. But how do you use that to see where f is 0? So if you think of moments, moments tell you where the function's large, not where the function's 0. So you might want to take 1 over f. So here Katz has a very nice idea. He says, let me use this expression here. Let f be non-singular and fixed. And if I look at the set of x such that f of x is less than epsilon, this is all in one variable, and there's a similar thing in several variables, divided by 2 epsilon, and I take the limit as epsilon tends to 0, and assume that f has simple zeros, this will just be the sum of a in Vf of 1 over the absolute value of f prime. So we can compute the sum over the 0 set weighted by 1 over the, this is called the Lalong differential. If any of you have studied the Hardy-Littlewood circle method, and you're counting solutions at the real place to Diophantine equations, the Archimedean contribution is this differential like this. So for any fixed f, which is non-singular, this is an identity. And now if I want to compute the expected value of this, and I can compute the expected value here, and now multiply by f prime to y to get rid of the f prime of a, this will compute the number of zeros. And then you have to just justify a simple switch of orders here, and then take the limit as t tends to infinity, and that's Katz's explicit formula. And this works with several variables identically. I won't write this down here, but this is a clumsy derivation. They're even slicker derivations. Clumsy derivations, by the way, are much better. Forget slick, because slick means you can only use it if all these slick things are in place, while clumsy is usually robust. And that's absolutely true here of Katz's derivation. This is Katz's original derivation. Since then, there have been millions of derivations, but it goes straight to several variables. And I want to tell you what will Katz's Rice formula compute in general, and it will never, unless you're lucky, be the topology. So in one dimension, the topology of a zero-dimensional set is just the number of points, the number of connected components. So it does compute that, and that's because the topology is so trivial. All right, let's go to several variables. So first, let me talk about a random projective hypersurface. So again, I'll introduce Pn. So I'm looking at homogeneous polynomials in n plus 1 variables of degree t. The 0 set is now a subset in, and it's extremely important, again, that I'm looking at real numbers. Because if you look at a typical complex curve, plane curve, you know what its topology is. The complex numbers connect everything up for you. That's what they invented for. But for real numbers, we are quite mystified. So V of f is the number of is the set of zeros, and that's the set I want to understand for a typical f of large degree. The Gaussian ensemble is, for any Gaussian ensemble, you can develop a Katz-Rice formula just the way I derived it before. You'll find this in many treatments. There's a book of Taylor and Adler, which has got probably the most general Katz-Rice formula you'll ever see in any setting. And it's quite useful. But what the Katz-Rice formula can compute, so I'm in several variables here, is not the topology, because the topology could be complicated, but rather the volume of the 0 set induced in the projective. You have P and R. You say I'm working here with P and R, and I'm taking the random Fubini Study metric, and I ask, what's the volume, the n-1 dimensional volume of this n-1 dimensional manifold? It's compact. the expected volume and its fluctuations. That's something you can compute with the Katz-Rice formula. As long as the quantity you're trying to compute is an integral of local quantities, you can compute it, the expected value, over the Gaussian by this formula. So for example, Euler characteristic, you can compute. You can compute the expected Euler characteristic of a random real variety this way in this Gaussian ensemble. In closed form answer, the only issue will be taking the limit as t goes to infinity, which is usually straightforward, at least for these Gaussians. And the reason you can do an Euler characteristic is because it's an integral of curvatures. So as long as an integral of local quantities, any topological invariant which is given by an index formula, which is an integral of local quantities, can be computed. The number of critical points of f can be computed easily. That's a number of points again. So anything that's local. But the topology, say the number of connected components, if you have a polynomial, homogeneous polynomial in 3 variables, I'm sitting in P2 and the 0 set is now a curve, I'll have a lot of curves. How many curves are there? That's not computable by Katz-Rice, and that seems to be extremely difficult. And in fact, it was not tackled until very recently. So that's a question I want to answer. Just to complete the story, the naive in several variables, the naive model is just the standard inner product. Here I have polynomials in several variables. J is a multi-index. It's the sum of the thing. It's homogeneous of degree t. So if you take a random polynomial in several variables and you take the coefficients at random, that's a naive model. You asked about the complex Fubini study, which has been hijacked by complex analysts. We're doing real analysis here, not complex analysis, but you can do some hybrid thing. You can make your model complex. Some people call this Bombieri norm, actually, because there's some norm he introduced with n-flow in some interesting functional analytic problem. It's as follows, that you take f and g, they're both real, you complexify them with the variable c, and you integrate against the complex Fubini study metric, and then you can compute what this is. And because z, when it's a complex number, is r e to the I theta, and because you have a theta integral, you still get that the monomials are orthogonal, which is completely different to the real Fubini study. And if you compute it, you'll find that instead of taking this naive inner product, you put the binomial coefficient, multinomial coefficient, and choose j. Mark Katz, who was very unhappy that he only had log t zeros for a random polynomial, said, I can see why I have only log t zeros, because they're all near plus or minus 1. So he said, why don't I make the variance of the middle terms in the polynomial be large? So let me choose the variance of the jth guy to be n choose j, which has a maximum in the middle and goes down rapidly. And then that was his second model. And it turns out to be it's nothing but the complex Fubini study model, if you homogenize. And in this model, you indeed have square root t zeros instead of log t. So he went from square root t to log t, but not to t over root 3. Of course, he could do t over root 3. That's his result, because he would just say, oh, no, that's trigonometric polynomials. That's a different subject. My method works for any one-dimensional set of polynomials, but it's a different story. So I'm going to only talk about the random Fubini, real Fubini study, because this is where there are most zeros, and this is the only natural one. And I want to show you that it's natural from another point of view, a much more general point of view, and that's where the title of this talk is about, what it's about. And that's a random band-limited function of which the random real Fubini study will be a special case. There will be a universality in a random function will have, a real function will have a universal behavior, and it will pick up on one end my monochromatic wave, and on the other end the random real algebraic geometry. So forget what I said for a moment, and now we just have a compact n-dimensional Riemannian manifold. Everything is smooth. I'm not interested in anything that's not smooth, but some of these scaling limits may be involved to non-smooth things. I don't know. I take an orthonormal basis of eigenfunctions. So this is a Riemannian metric, so I take an orthonormal basis of the eigenfunctions of the Laplacian on functions. That's all I'm looking at here. I'll write the eigenvalue as tj squared. It's much more convenient here. And you might say, what happens if there's a multiple eigenvalue? What orthonormal basis do I choose? I'm going to define a family of finite dimensional Gaussians, which will define my random function on this manifold. It's going to be called Bandlimited. I first picked up Bandlimited from Nash, actually. In his Nash embedding theorem, he describes all these embeddings in terms of filters, and when he wants to cut a Fourier series, he says you make a band-limited function by cutting the Fourier series of high frequencies that you remove. It's an engineering terminology, and it's very apt here, as you'll see. So there's only one parameter in this band-limited. M is a fixed manifold. In the end, nothing will depend on M. It will only depend on this parameter alpha. So choose a parameter alpha between 0 and 1, and I'm now going to define for you a Gaussian, which will be a generalization of the polynomials, homogeneous polynomials of a fixed degree. So EM alpha of t is the following Gaussian variable, the Gaussian vector space of functions with a Gaussian, which is defined as follows. I take f of x, which is a linear combination of the phi j's, where the phi j's are my orthonormal basis, and I band limit the eigenvalues to be in a interval between alpha times t and t. So if alpha is 0, I'm summing all the frequencies up to t. If alpha is t, you might say I'm summing on nothing here. But there's a convention that if alpha is t, then I open a window here. It's a micro-local window. I don't want to get into technicalities. I'll show you where this is relevant. But the tj's go from t minus something which is still going to infinity, because I don't want to, you could even have eta bounded, but that would be pushing these techniques to their limit. So eta will go to infinity, but of course eta of t must be little o of t, so that the shell, the annulus, has now become a thin shell. So from what will emerge, the only thing you need to know is alpha. So the one extreme, alpha equals 0, I'll show you, is our random Fubini study and real algebraic geometry. Alpha equals 1 is going to be the monochromatic wave. If alpha is 1, we are taking all the frequencies, all the Laplace eigenvalues, to be the same size. And that's the notion of a monochromatic wave. These are waves all with the same energy. And so the question is, what does the zero set of a random wave look like? And what does the zero set of a random algebraic equation look like? Those are the two cases. Now, why is alpha equal to 0? At least on the face of it, it'll contain what I spoke about before. And in the end, by universality, it'll be the only answer. So if you take, there are very few manifolds for which you can write the eigenfunctions down. Take my word for it. I've spent most of my life just writing down eigenfunctions. So did Gelfand, yeah?
This doesn't depend on phi.
Now, so the actual Gaussian distribution does not depend on. That's an easy exercise. So this is completely canonical. So you take any orthonormal basis. If you choose another orthonormal basis, the measure on the space of functions will just be, there'll be a unitary transformation from the one to the orthogonal. Unitary on this. Okay, so there are very few manifolds for which you can write the eigenfunctions down explicitly. And one of them is the projective space with its round real Fubini Study metric. After all, that's the n-sphere. What?
Sorry, can you do this on a manifold with a boundary at all?
Yes, but I haven't. I haven't given that much thought. I don't think the boundary will have much impact. I could explain that afterwards. We're counting what's, at least, okay, the question is what question you're going to ask about the zero set. If you're going to ask me how the zero set looks near the boundary, of course, that's a different story. But if we can ask what the zero set looks like in the interior, the boundary will have no impact for reasons I'll explain. So it won't change much. All right, so the if I take the standard projective space with the round metric, which you could think of as taking the sphere with its standard round metric, just the round metric that it comes in Euclidean space, induced metric, and I make that's a compact Riemannian manifold. Then, if any of you have looked at this with any serious, I'm sure all of you know that the homogeneous polynomials, which are harmonics, so-called spherical harmonics, are the eigenfunctions of the Laplacian on the sphere. So if I take alpha equals 0 in this model that I've just given you, and a simple representation theoretic calculation will show you the ensemble that I was talking about, the real Fubini Study ensemble, is no more and no less than the alpha equals 0 here, where the eigenvalue, where the number t will depend on the eigenvalues of the Laplacian for spherical harmonics that are explicit numbers in Rn. So the random real projective geometry hypersurface question is none other than this question of alpha equals 0 for this particular manifold. And the alpha equals 1 is the most important thing in this eigenfunction case. It's the monochromatic ensemble. I'm going to show you pictures in a second, so you'll see that these are quite different. So we look at the 0 set. We're now in several variables, and I want to understand the topology of the 0 set. So let C of S denote the connected components. Now here's where things are very different over the reals and the complex. I'm going to take a typical member in this ensemble, and I'm going to look at the 0 set, and the claim that will be substantiated due to work of Soden and Nazarov in a minute is that there are many connected components. There won't just be one connected component. The typical F will have many connected components. And I'm interested in the topology of this 0 set, which means it's a union of its connected components. And we could ask, what's the topology, typical topology that we see? So I'll write the 0 set as a disjoint union of its connected components. You might worry that the components cross, touch. No, none of that happens for a typical F. So I'm interested in what's happening for a typical F only, and those aren't issues. I take the manifold, now subtract, remove the 0 set. That breaks up the manifold into connected components. These are closely related things. These are called nodal domains in the theory of eigenfunctions. I'll call them nodal domains. People who've studied real ovals and real algebraic geometry certainly study the connected components of the complement of the 0 set. So C of F will denote the set of components of the 0 set. Omega of F will denote the set of nodal domains, of which a certain finite number. And I'm interested in what is the distribution of the topologies of C of F and of omega of F in the space of possible topologies. Okay, I promised a picture. And this is, if you take nothing from this lecture, take this beautiful picture due to Barnett. Barnett has taken, firstly, I like this light shining in there. There's a little bit of art to the picture. What he's done is this fellow's at Dartmouth, and he's the best guy to compute highly excited eigenfunctions and real polynomials, which is what's here. So he's taken a random real polynomial of degree 80 on the projective plane or on the sphere. This is what its 0 set looks like. And if you takes another random guy, your eye won't be able to tell the difference. It always looks the same. So these are the connected components. These are the nodal domains. The boundaries are the ovals. They are the 0 set itself. These things don't cross. So if they look like they cross, it's just because they don't cross in practice. And we know they won't with probability 1. Okay, so we want to explain that picture. And as you can imagine, when the degree gets bigger, so how many connected components does a random curve have? So you can count in this example. He does. You'll see the answer in a minute. And that's a random monochromatic wave. Looks quite different from some point of view. It's a little more structured. It's the 0 set of a random spherical harmonic of degree 80 exactly. So this is where the shell, where all the frequencies have the same energy. And the question here is, well, all right. You could ask how many connected components are there. You could ask how many nodal domains are simply connected, how many are doubly connected. You can ask any question you want. We can answer almost no questions. One of the things here which got me into this was an issue of whether this is connected to, in this two-dimensional case, to SLE, some amazing, wild conjectures of Bogomolny, all of which seem to be wrong now. I'll tell you a little more about that. Okay. So this, I wouldn't be talking here if there weren't a breakthrough. And Soden, Nazarov and Soden introduced a tool. These are soft tools. Their paper from some 4 years ago, which is when Wigman and I started to work on this, were quite complicated. They were using lim subs and lim ems. There was no sort of structure. They've since put on the, well, they haven't published anything, but they put on the archive a lecture which simplifies, makes it a lot softer. Anyway, their tools are fundamental to anything Wigman and I will do. Without their tools, we wouldn't be able to start, because the problem is not at the level where Katz and Rice can say anything. What Katz and Rice will control various things. For example, the number of critical points can be controlled. I told you can compute the expected number of critical points. Well, by Morse theory, that'll give you an upper bound for the Betti numbers. That'll give you upper bounds for the topology of some type. In other words, you have to do some surgeries to get the real manifold you're looking at, and the number of surgeries is bounded. That can come from a Katz-Rice formula. But the number of topological types that a surgery can create is infinite in high dimensions, so that doesn't help that much. So what they have studied is just the simplest thing, and that's the number of connected components of a real algebraic variety. Their methods are written for another purpose, so I'm going to say their work easily allows us deduction, which is true. So let me state their theorem. The theorem is for a random band-limited function in the setting that I've given you. So I have my manifold M. I have these ensembles E, M, alpha, T. T is going to go to infinity, and I'm asking what's typical for what's true for a typical F. And the answer is the number of connected. There is a constant for each M, N, and alpha. The constant doesn't depend on the manifold, only on the dimension and that band-limited quantity alpha. It's positive. This is probably the hardest thing in their work. So there's some soft stuff that gives existence. So this is quite well known in statistical physics. If you can get some kind of ergodic theorem to work for you, you'll get the existence of a limit, but you'll know very little about it. Then you have to create configurations that are favorable to show that something actually happens. So the positivity of this constant is perhaps the most interesting thing in their work, although the soft methods are very powerful, such that the number of connected components is asymptotic to this non-zero constant. Of course, if that was zero, it would be quite useless, times t to the n. So I'm telling you that in any one of these models, any manifold, the number of connected components of a typical F, this is for a typical F, obviously the Fs for which, with very small probability, you could find Fs doing anything you want. But they are Fs, the typical F will have a universal asymptotic distribution of the number of connected components. So in that picture that you saw here, I'm going to discuss this. I'm going to call these the Soden-Nazarov constants. So in this picture here, where the degree, this already kicks in here, the degree is 80, the number of connected components, which you're welcome to try count, will be close to some number times t to the n, which in this case will be very close to the degree squared, a constant times the degree squared. I'll tell you a bit later what that constant is, thanks to other experiments of a student of mine, undergraduate here at Princeton a couple of years ago. All right, to save time, yeah.
The picture sort of seems to remind me when people do what's called quenching. They take a high temperature mixture and they quench it, and they look, they take a cross section of a three-dimensional thing and have some ideas about Fourier components being all of the same magnitude, but
so if they're random, if the function was made out of a random series, so one of the manifolds that's perfectly kosher for this is a torus. So a Fourier series, and you take the eigenfunctions, and you take a monochromatic band limit according to the rules I gave you, a certain width. I'm about to tell you there's a universal answer. They've shown already there's a universal answer for the asymptotics of the number of components. I want to actually study what are the distribution of the components. Okay, so let me describe this. I wanted to describe, this is inspired by Hilbert's 16th problem. Hilbert got very interested in work of Sarnak. Sarnak considers a real polynomial of degree, homogeneous polynomial in 3 variables of degree t. And Sarnak's theorem is that the number of connected components, there are many proofs, in the complex numbers, we know the genus of such a generic curve. Over the reals, he shows that the number of ovals, they used to call them ovals, the number of ovals, the number of connected components is at most the integer part of t times t plus 1 over 2. And ovals which achieve the maximum are called Sarnak curves after Sarnak, because Hilbert got interested in how to achieve ovals which have a maximum number, curves with maximum number of ovals. And he pointed out that Sarnak's construction gives some very simple nesting type, and he produced a second nesting type, and he asked if these are all the nesting types, and that became Hilbert's 16th problem, a solution of which still it's not clear. It's false what Hilbert was hoping for, but just exactly what the solution is. It's a very popular subject under Arnold and his school. And the question then is, what about a random curve? How many ovals does it have? Or what's the nesting of a random curve? So I'm just going to save time and not describe to you the statistic which is connected with the nestings, which are called the end of the nesting graph of the zero set, but that's one of the cases. I just want to save time and stick to what we can do. Okay, so now I'm going to finally state a theorem and then discuss its proof a little, very little. So for each f in any of these ensembles on any one of these manifolds, and t is very large, and the band limit, the alpha is fixed, so I have my ensemble M alpha t, so it might be a random real projective hypersurface. I'm going to define the following measure. Firstly, for each connected component, the topology of that connected component is a topological type in the space of topologies of compact n-1 dimensional real manifolds. Okay, you might ask me, what's that space? Of course, nobody knows. But it's countable. Everything's smooth here. You can triangulate. There's a countable number of topological types. In low dimensions, we will look at this. In high dimensions, I can't describe the set to you, but that doesn't mean we can't work with it. So I'm going to put a delta mass at each topological type, and I divide by the numbers. I'm putting a probability measure on the space of topological types of n-1 compact manifolds. Okay, that's a measure. So each f in my ensemble, which is non-singular, which almost generic f's are, gives me this probability measure. And as t goes to infinity, of course, I'm going to state a theorem in a minute that these measures converge to a universal measure, and I'll tell you a few words about it. I don't know much more about its existence and some very small properties. So this is a measure on the space of topological types. Similarly, the nodal domains will give me a measure on the space of all n-dimensional manifolds with boundaries, smooth, which again is accountable in the set of topological types. By the way, people like Betty numbers, right? So this is a much finer theorem. I'm going to describe a universal distribution of topologies. That implies there's a universal distribution of Betty numbers, of the vector Betty numbers in particular. So the point about these methods, they're so powerful that they can actually give much more. So I won't describe the nesting graphs, which turns out to be a measure on the space of rooted trees. But let's stick to these. So this is a measure on the space of topological types, which I denote by hn-1 tilde. And these are a measure on the space of n-dimensional manifolds with finite, with boundary, which are everything being compact and finite type. I'll return to some low-dimensional examples in a second. So notice these are measures on these non-compact countable spaces. And now I can state the theorem. I think I learned that Mumford would state a theorem with a little t, which means that it hasn't quite been checked, but this is much more extreme. This has not been proved. The exact proof, what we can prove is on the archive and much more, so that's why I'm going to add here, but it's...
I think there's a convention, you take the T away, call it the E away.
Okay. The cases that are proved are in a preprint that Wigman and I just put up a month ago. In that paper, there's some questions of which we can now resolve quite a few, but not every single one of them, and I'm stating it here just for convenience as if we resolved every one of them. So that's what the star means, and the little t means the usual little t, meaning modulo writing it up. Anyway, the methods are quite robust. There is a universal measure depending only on alpha and n. So on the band limit and the dimension, such that the topological types are the measure which each f, typical f, will converge in a sense that I'll describe in a minute. So there are these measures. It's a probability measure. That's a very non-trivial statement there, because these spaces are non-compact. It's a probability measure on the space of topological types of dimension n-1, which depends only on alpha and n. There's a similar thing on the space of manifolds of dimension n with boundary. In both cases, the topological type must embed into Rn. So if you think we know a lot about 3 manifolds, well, I don't know much, but we know if you think that mankind knows which 3 manifolds embed into R4, this is completely open. There seems no easy description. Anyway, everything that will appear in the support of this measure will be embedded into R4, because something will be localizing and will be in R4. If you were 3 manifold, you would be in R4. So instead of having the space Hn tilde, which was all topological types of n-1 manifolds, this tilde is removed. It's ones which are embedded in Rn, and similarly here in Rn. Of course, if you're proving a theorem like this, something had to become local, and that's what's the case. Forget the nesting types, such that if you take T large, then the typical F, typical in the sense that the discrepancy of the measure that your 0 set will give to this universal measure, the ones that are bad, bigger than epsilon, tends to 0 as T goes to infinity. So this is a weak law of large numbers. It's no more than that. It's like a weak law of large numbers, meaning every typical F, when Barnett does this experiment, he throws in an F in low dimensions, he always gets the same count. This theorem that's this theorem in action. I'll show you what it looks like for his cases. And what do I know about this measure? A, it's a probability measure. That's hard work. And the second thing that's very hard work is that it's supported on every topological type that it can be, that it charges every one of these atoms. So there will be, you give me a topological type which embeds in Rn, this universal measure that is the distribution of your random hypersurface will charge, it will occur with some the estimate for the probability is tiny, but it's positive. So the support of these measures is the entire set of topological types which embed into n-1 dimensional space, Bn, and these are rooted trees. So that's our theorem. And these universal laws imply that there's a universal distribution of the Betti number of the 0 set of a random real projective variety. So you take a random real projective variety and you, in dimension n, upon Carré duality, the Betti numbers, so it's connected, so the first Betti number is 1, the 0th Betti number is 1. And you only need to know up to the middle dimension. In the middle dimension, there's a bit of a tricky thing about intersection. Turns out that we can show, there you need a little bit of topology. In the middle dimension, it's always even. And then you give me any vector, and you ask how many of the components have this as its distribution of Betti numbers, and the answer is there exists a universal probability that you'll hit that, and it's positive. That's all I know about this universal measure. I don't know how to get any further information from the technique other than to Monte Carlo. Now, there were some works after Nazarov and Soden, some before and some after, some using Katz-Rice formula, which is upper and lower bounds for the Betti numbers, the expected value of the Betti number of a random such guy. Now, the upper bound for the expected Betti number can be gotten by Morse theory and Katz-Rice, which gives you an upper bound for the number of critical points. A lower bound is using this technique of Soden and Nazarov of construction of barriers, and was done by Guyot and Walshinger, and later by these two fellows, Larerio and Lundberg. But that's just the expected Betti number. That's the mean of this measure, of which I'm telling you there's an entire distribution, which is much finer information. All right, so just to show you this is very concrete, at least when I know what the topological types are. Otherwise, it's not concrete at all. It's just existential and some extra properties. So for n equals 2, so I'm looking at the random 0 set. So in dimension 1, Katz cleaned everything up. In dimension 2, the 0 set is now a bunch of ovals. They don't cross, so the topology of the 0 set, each oval is a circle. So the only thing you need to know the topology There's only one circle in the world, topological circle. So the only thing you need to know is the number of components, and that is given by Soden and Nazarov. So the distribution on H1 is the topological types of connected compact one manifolds. Well, this is just a point, so there's no interesting equidistribution. But if I take B2, that's a set of planar domains. Remember, they have to be embedded in the plane. The set of planar domains which are finite type. So up to topology, those are determined completely by their connectivity. So if you ask, I give you an eigenfunction in the plane, and I've got a random model here, how many ovals does it have? How many nodal sets are simply connected? How many are doubly connected? Our theorem says that there's a distribution that's universal that depends only on alpha. So if you a random plane curve in the real Fubini study, it'll look like one thing. If it's a random monochromatic, it'll look like something else. So B2, the space on which we're becoming equidistributed in this case is just the integers, and that's easy to describe the space at least. And if you take, and Barnett has calculated for those examples what these measures are. Every time he runs, it's the same. So this is worth knowing. If you take a random real plane curve, so this is alpha equals 0, Fubini study, the number of connected components, the number of ovals, the number of nodal domains which are simply connected in that picture will be about 93% every time. The numbers which are doubly connected, and here you see the theorem in action that everything is charged. But it drops off. I don't have any formula for this. It'd be lovely if there was some percolation explanation. Nothing we understand. So as far as numbers go, only through numerical experiment. In fact, what Nastazescu did, which was quite beautiful, is she computed the number of connected components and estimated the Soden-Nazarov constant for the random real Fubini study. And it turns out that it's about 4% of the maximum. So your random plane curve is 4% Harnack in the real Fubini study. Remember, the random real polynomial is 1 over root 3. The number of zeros is 1 over root 3 times the maximum. The number of ovals of a plane curve in the same real Fubini study is the 1 over root 3 is now replaced by 4%. And that number is what Bogomolny predicted from an exactly solvable percolation model by Yang Baxter and Lieb. This was an exactly solvable model of bond percolation in a standard lattice, which is not universal. And he predicted the number that Nastazescu found, and the answer was good to 3 decimal places. I believed him for a few years, but Barnett went much further in his student, and this number, which was 3, was off in the 4th decimal place, didn't get better, it only got worse. So it's amazing that he predicted the number with, so this 4% can be predicted with some accuracy, but I don't think it's true. And nothing seems to indicate that that's true besides just the number. All right, I have 7 minutes. I thought I would have 20 minutes. I want to explain at least where these things are coming from, because it's quite remarkable that there's a universal distribution of topology. It's something I would never have expected. Something is localizing, and I want to explain to you, if it doesn't localize, something's really global, then it's real probability theory. By the way, so if you ask, what's the longest component? So you're not asking for something, what's most of the components looking like, but is there a long component which visits the whole of projective space? So these are other kind of percolation, like the biggest connected component, the longest connecting two things. Those things may be connected to percolation theory, but those, we have no clue about saying anything. Anything.
Does he see them numerically?
This question has not been experimented numerically. So Bogomolny thought he was predicting the number of connected components, but it's wrong. I think these other questions that you've suggested on a number of occasions as being more universal from percolation point of view. Notice the theorem has nothing to do with 2 dimensions. So I'm not using any percolation anywhere in any thinking. All right. So I told you that the covariance, which is the expected value of f of x times f of y, is a critical input. I want to explain firstly why things don't depend on the manifold and why they may localize. So if I were doing a cat's rice calculation, I would first compute the expectation of f of x times f of y, which if you just write out through that sum, the definition of f, it's some aj, phi j, another one, and you use independence and Gaussian. Well, it doesn't have to be Gaussian for this. You'll get k alpha t x y, which looks like a complicated expression on my Riemannian manifold. It's the sum over all the eigenvalues between alpha t and t. Imagine that I put x equal y and integrate. Then I would get just counting the number of eigenvalues. So what's the dimension of the space? Well, there's something called Weyl's law, which gives you the asymptotics of the number of eigenvalues in an interval, and I've chosen those intervals sufficiently fat so that you can do micro-local analysis. That's exactly why I chose it. And it was Weyl who understood that this universal Weyl law only depends on something local, which you then integrate up, and that's how he proved Weyl's law. And so we need to develop something like that in order to understand the asymptotic behavior of k alpha txy, because this is the key thing controlling things. All you need is, okay, so Weyl, as Weyl proved it, would not be good enough to do this kind of band-limited stuff. But today, with hindsight, with understanding how to deal with Weyl's law, all we need is actually the ingredients done by Peter Lax, 1957, the construction of a parametrics to some accuracy to the wave equation. I won't go into that, but that's the micro-local analysis. This is pre-Fourier integral operators. So the famous paper of Homunda was just developing Lax's ideas in the context of a manifold. Lax worked, of course, in Rn. The manifold was for very fancy people. So anyway, with this construction of parametrics, you can prove, so whatever I'm going to do, if I'm going to compute critical points or anything to control this, I will need to understand what happens to this ktxy when t goes to infinity. And that's where the universality is going to come in. So k alpha txy divided by the dimension, that's just the sum of the number of these guys here. When x and y are on the manifold, has a universal behavior. That is, it's some universal function of t times the distance, the Riemannian distance from x to y, if the distance is 1 over t. So if x and y are very close, within 1 over t of each other, there's one universal answer. And if they are very far apart, things are uncorrelated. So this tends to 0, like at least 1 over t, when x and y are just a little bit apart. But when they're very close, it's controlled by a universal function which has to do with this band limit, which is why the universality comes in. So that function, which is a function on a vector in Rn, actually only a function of the length, is the Fourier transform normalized of the characteristic function of the annulus. And if alpha is 1, it's the Fourier transform of a sphere, which is something that's a Bessel function or an integral of the Bessel function. So this Bn is a well understood thing coming from micro-local analysis, and there's no, at this level, and if all the components are going to be happening at roughly size 1 over t, their diameter, and I'm saying that most of the components are very small in this sense. This is going to be true. This is the key insight of Nazarov and Soden. And we use their methods and generalize them, and they need serious revision for this equidistribution, but their ideas are what lead the way. So if most of the components are this small, then you could imagine that the theorem's becoming local. And because things are uncorrelated, this is why you have a very strong law of large numbers, because at different spots, they don't know about each other. So it's as if you just count how many there are here, how many there are here, how many are there. You're sampling independently, so you'll get a this is where the universality and concentration about the mean comes. But in computing this limit, whenever you do some kind of scaling limit with a cone blowing up, now you blow up with size 1 over t here. Remember that in the previous slide, this was distance 1 over t. You get, and this is where all the answers lie, you get a Gaussian, and it's not the free field. And this is why this question is not properly connected, at least in dimension 2, to, I want to explain this point because I was misled by this myself many years. You're led to the following infinite dimensional. So we had a finite dimensional, we're taking t go to infinity. I'm now going to give you the key infinite dimensional Gaussian, which controls all the answers. There'll be 1 minute. And that's the following. We take an orthonormal basis of the functions, for the functions, any orthonormal basis, for the functions on the annulus or on the sphere, And we take their Fourier transforms and we make these CJs IID Gaussian mean 0. So this sum here, because the function, these functions here are supported on the sphere, this Fourier transform are actually decaying fast in J. So for x in a compact set, this function f of x here with typical CJs, this is by simple Kolmogorov type argument, these are analytic functions. So your typical member in this ensemble is an analytic function, and its 0 set is what's important in the scaling limit. You have to relate the two. What's extremely important is that there's an action of Rn, this limiting Gaussian on Rn, which is now on Rn, is translation invariant. So you have an action of Rn, and there's a certain ergodic theory you can apply. I won't go into it, but that's why the existence of various probabilities.
Sorry, what's psi cap as compared to psi?
Fourier transform. So this has a certain reproducing kernel, and this makes your typical member in this ensemble analytic. You saw that structure, that it wasn't completely wild. So the Gaussian free field is supposed to be a generalization of a Brownian motion to higher dimensions. Then the typical guy is supposed to be wild, nowhere differentiable. These are analytic. This is why we can answer all these questions. And it's in these guys that all these mysteries, all the answers, the existential questions are now referred into this space. So the hardest thing is then to prove properties of those measures. Let me end with a picture made by this young man here, Matthew. Now I've run out of time. You can find the paper on the archive, which explains all the new ideas to prove properties on them. Any final properties on the measure require hard work. The path to get to that point with softer arguments has been paved by Nazarov and so on. But if anything, there are more questions you can ask here than answer. And the one thing I can tell you is there's a universal distribution of topologies of a random variety, something I find quite striking. Thank you.
Thank you.